Welcome everybody. We're going to work today with inequalities in two triangles. You've already learned how to use the triangle inequality theorem and a couple other theorems to compare sides and angles with one another within a single triangle. Now we're going to look at comparing measurements from one triangle with measurements from another triangle. And in particular, you're going to use what's called the Hinge Theorem and the converse of the Hinge Theorem in order to compare measures in two different triangles. All right. Now, the things that we learned about a single triangle and how you know where the longest side is and so forth don't work whenever you're talking about two different triangles. For instance, if you look at this triangle ABC, we know for certain that since this is a 90-degree angle, that side opposite that is the longest side in the triangle. Okay? And so if I had a 60-degree angle right here, for instance, you would know that the side opposite that, AC, would not be as long as side BC across from the 90-degree angle. All right, but how about when we have two different triangles? You can see angle A in this triangle is 90 degrees. Angle D in this triangle is 60 degrees. Can we then say that the side across from the 90-degree angle right here is longer than the side across from the 60-degree angle? Well, there's some logic to that, but you can clearly see that segment EF is longer than segment BC. So it's not as simple when you're trying to find whether one side in one triangle is longer than another side in another triangle. It's not sufficient to just merely look at the angle measure opposite the sides that you're comparing. There's got to be some other information that is required before you can make such a comparison. All right, so let me show you this then. Here I've got two triangles where it turns out I can compare a side between them. Now, in order to be able to compare a side with one triangle and a side in another triangle to see which one's longer without actually knowing the side lengths, you have to have two sides that you already know are congruent to one another. You can see there's a 3-unit segment and an 8-unit segment in each one. All right, now this circle is just to show you that they actually are the same because those are arbitrary numbers. So let me move the circle over here so you can see that indeed I'm centering it around point A there. You can see that segment AB in the top triangle is congruent to segment DE in the bottom triangle, right? And then since the side AC and DF are horizontal lines, you don't need me to do anything in order to compare those. You can already see that they are actually 8 units long the way that I said that they were. Whoops, let me move that out of there again. Okay, so I've got the two sides of the triangles are congruent, and I'm trying to figure out which third side is larger. Well, when you have two sides that are congruent, you can use the included angle of those pairs of sides to determine which third side must be greater. You can see that the hinge angle, or, well, I'm saying hinge, I want to use that term later. The included angle of segments AB and AC is an acute angle, isn't it? The included angle of segments DE and DF is an obtuse angle, so clearly it's larger. And since everything else is equal, the fact that this included angle is larger makes the opposite side from that angle longer than the opposite side from the included angle in the other triangle. All right, what I'm describing to you is called the Hinge Theorem. And the Hinge Theorem assumes that you have a pair of triangles that each have two pairs of congruent sides. So in this case, segment AB is congruent to segment DE, segment AC is congruent to segment DF, and if both of those things are true and the measure of the included angles of those pairs of sides, the first one A, is less than the measure of the other included angle, D. All right, if this one is less than this one, then the sides opposite those angles, the third sides of the triangle, have to have this relationship. BC would have to be less than EF, because everything else is the same, but it's across from a smaller angle than what EF is. Okay, now it's called the Hinge Theorem because you can kind of imagine the angle between these two pairs of sides as working like a door hinge. And the wider I swing this angle, the further this point B gets from point C, and so the longer this opposite side would get. All right? Whereas if I were to take that hinge angle and I were to close it in, then that point E down here, for instance, would get closer to point F, and so the length of the third side would shrink. All right, but that doesn't matter if the sides of the hinge angle are not congruent to one another. All right, now there's also the converse of the hinge theorem that we need to talk about, and that's a way that you can determine when triangles have two pairs of congruent sides as these do. You can determine whether the included angle of this triangle is larger or smaller than the included angle of those congruent sides in the other triangle. Okay, now one of the things I had to do a lot in this video is kind of highlight the congruent sides so you can see what the hinge angle is that we're looking at. So those two sides are congruent to these two sides, and then we want to compare and see whether this angle is larger than this angle. Now a lot of times these are fairly obvious, but you have to go by the numbers, not just by the way it looks. And you can use the opposite side, 12 and 5, to notice that this angle is bigger than this angle since everything else is the same. All right, so the converse of the hinge theorem would tell you that if triangles had two pairs of congruent sides and the third side of one is larger than the third side of the other, the included angle for the first triangle is greater than the included angle for the second triangle. I'll write that out in terms of segments and angles here. All right, so if you got the two pairs of congruent sides and the distance from A to B is greater than the distance from D to E, the length of this third side is greater than the length of that third side, then the included angle of the first one is greater than the included angle of the second one. Or in other words, the measure of angle C has to be greater than the measure of angle F. All right, let's apply this in a few problems. First couple of examples are going to be asking you to complete a comparison between two measurements, sides or angles, with an inequality or a symbol or an equal sign. All right, one or the other. And it wants us to explain. All right, now we're comparing an angle from this top triangle, angle HFK, with an angle from the bottom triangle, angle MFK, and we want to see which one is greater. Well, since those are in two different triangles, the only way we can compare them is if those triangles have two sides that are congruent to one another. Now, if you look here, this pair of sides is congruent to this pair of sides, isn't it? By the reflexive property, segment FK is congruent to itself, and it's marked that segment FH is congruent to segment FM. All right, so based on that, then, we can make a comparison between the two angles that we're asked to make a comparison for right there and right there. Now, they're not equal to one another because the triangles weren't congruent. Otherwise, well, I'll leave it at that. What we can tell, then, is that the third side of the top triangle is longer than the third side of the bottom triangle, so the included angle between the congruent sides here greater than this one. So HFK is the larger of those two measurements. We'll put a greater than sign right there. And this could be your explanation. All right, the sides of angle HFK are congruent to the sides of angle MFK. I was just generalizing that a little bit to make it make more sense verbally. However, the side opposite angle HFK right here is greater than the side opposite angle FMK or MFK, which is right here. All right, that justifies why this is true. Great. Let's do another one. Here, we are again comparing measurements in two different triangles. TR from the top triangle. We're trying to compare to NV from the bottom triangle. And we know that those triangles have two different sides that are congruent. The side that they share and that side right there are congruent to these right here, okay? So that 74-degree angle and the 70-degree angle there are the hinge angles that we're looking at. And the two segments right here, then TR and NV, are the sides opposite the hinge angles. And so we can conclude, of course, then that NV is the larger of those two, or if we're using our inequality statement, that means TR is the lesser of the two because the hinge angle opposite TR is less than the hinge angle opposite NV. All right, you could write out a similar statement to what we did a moment ago. All right, one more problem here. we're going to want us to write and solve an inequality to describe a restriction on the value of x. Okay, now take a look at these triangles, and you're going to see the same situation in these triangles that we had in the others, where we've got two sides that are congruent to one another. This pair of sides in that top triangle are congruent to this pair of sides in a bottom triangle. You see the two that are 9, and again the reflexive property, this right there, is what they share. Okay, so the hinge angles that we need to compare to see whether the third side of this triangle is larger than the third side of this triangle are this angle and this angle. Now, it would be impossible for us to determine what the measure of this angle is right here, exactly with the information that we're given. However, we can conclude that it's not as large as 80 degrees, right? Because if this is 107 degrees, then 80 degrees would put this triangle over 180 degrees. So, it's guaranteed that this hinge angle is smaller than this hinge angle, which means that then 2x plus 3 has to be greater than x plus 8. Now, using that logic then, we can make the exact inequality that is read. 2x plus 3 is greater than x plus 8. And then we can conclude by using algebra that x is greater than 5. Subtract x and subtract 3 from each side of the inequality. Now, are there restrictions on how large x can be? Of course, but generally speaking, we know that it has to be greater than 5 in order for this distance to be greater than this distance. All right, and just to show you why that was true, let's say we pick something that's bigger than 5, like 7. Well, if this is 7, if x is 7, then this would be 17 and this would be 15, right? Whereas if I picked something like 4 that doesn't make this true, this would be 11 and that would be 12. And so we would have the wrong segment being longer than the other. All right, that's how you use the hinge theorem and its converse. We'll talk more about it in class. Thanks for watching, guys. See ya.